Hello, my name is Minyoung Hwang. I'm a graduate student from the Department of Electrical and Computer Engineering at Seoul National University. It's a great honor to have an opportunity to present my research in this session. Today, I will brief you on my research on geometric understanding of reward function in multi-agent visual exploration. Robot navigation in a novel environment has been developed with metric-based and visual-based methods. In visual navigation, most of the prior works were based on single agent, and it hasn't been a long time since multi-agent was used in research. When multiple agents navigate together, it is much more difficult to train them than the single agent case. The purpose of our research is to find an effective visual navigation method for a multi-agent system. Especially in this research, we try to solve a visual exploration task in a novel environment, training agents to explore as much as they can and as quickly as possible. A direct extension from single-agent reinforcement learning is to consider each agent as a single independent agent and apply independent Q-learning algorithm. Although it is possible to train agents with this approach, we cannot guarantee whether agents cooperate or not. Due to the partial observability between agents, an agent might search an area previously searched by another agent. Additionally, they can follow similar trajectories if their current positions are close enough because they use the same policies. This partial observability problem can be solved using centralized training and decentralized execution, which is called as the ZTDE framework. Using this framework, agents are trained with access to centralized information during training time, but execute their actions based on their local observations. We develop a batched actor critic model based on PPO algorithm, and our centralized critic takes every agent's action and observation as input. Still, there exist two main problems of multi-agent RL for the exploration task. The first problem is mutual overlapping between distinct agents. This mutual overlapping coverage corresponds to the area that are covered multiple times. The second problem is self-overlapping for each agent. When an agent wanders around a local area with repeated actions or does not spread from the initial position. These two problems imply that the multi-agent visual navigation necessarily needs visual aspects and geometric understanding of the environment. Therefore, we designed the reward functions understanding the geometric manner of visual navigation. Instead of calculating credits of agents in global reward, we assigned individual rewards regarding other agents. This is because credit assignment of a global reward requires high computational cost in photorealistic simulation environments. Prior studies about multi-agent reward shaping suggest that reward shaping methodologies have the potential of improving learning speed and performance, and therefore we designed mutual overlapping and self-overlapping rewards to reduce the overlapping issues. The total reward function we proposed is described as this equation. Now, let's look at how we designed the mutual overlapping and self-overlapping rewards. First, mutual overlapping reward encourages agents to exclude multiple counted regions using the inclusion-exclusion principle. Considering n agents, notation R sub t indicates an n-sized real vector composed of each agent's reward. We focus on the exploration reward RT-explore in our approach. Simply, exploration reward can be given as the area that each agent explored. However, that kind of definition considers not only newly discovered areas, but also previously discovered areas by at least one agent. Therefore, we divide the exploration reward into two terms, non-overlapping reward and mutual overlapping reward. We subtract this ROT term to penalize the mutual overlappings. We designed two different models for mutual overlapping reward, linear and exponential. And for convenience to compare with the agent without mutual overlapping reward, we denote 0 as RO1 model. In the experiments part, I will compare these three different models of mutual overlapping reward. Next, we designed the self-overlapping reward into three different models. We used geodesic distance, which is calculated as the shortest path distance between positions to express self-overlapping coverage. Global self-overlapping reward encourages each agent to spread from its initial point. The first two models express global self-overlapping reward in two ways. On the other hand, we added local self-overlapping reward on the third model, which trains agents to get out of a local area when they are stuck in a place. Now, let's look at the experiments. We set the task as maximum coverage visual exploration, where agents need to cover areas together as much as possible and as fast as they can. In the experiments, we fixed n as 2 and defined the discrete action space for each agent as shown below. We used Habitat Simulator, which is a photorealistic simulator with Gibson dataset. For fair comparison, every network in our experiments is trained end-to-end for 10 million time steps without pre-training. More details for training and testing are shown inside the blue box. We conducted two experiments to shape the reward function with its geometric understanding. In every experiment, we used our multi-agent baseline network and only changed the exploration reward function. In experiment 1, we compared linear and exponential mutual overlapping rewards against the base policy, which doesn't use any mutual overlapping reward. Table 1 shows the different characteristics of each type of model. The second experiment uses both mutual overlapping and self-overlapping rewards. Since we fixed the ROT as the optimal mutual overlapping model from experiment 1, we just compared different types of self-overlapping models, as shown in Table 2. Generally, in many reinforcement learning algorithms, we use average reward as a training metric. But in our research, because we shaped the reward function manually, we used the coverage ratio as the training metric. We also use this coverage ratio and average time steps as evaluation metrics. Now, let's look at the training graphs. The colors are matched with the reward functions used for models, and this graph shows that the green one, which corresponds to the combination of RO star and RS3 model, shows the highest training performance and fastest convergence. Now let's look at the results of experiment 1. In the first experiment, comparison between mutual overlapping models are described in Table 3. Among the three models, RO2 model, which uses linear-shaped mutual overlapping reward, showed the highest performance in both evaluation metrics. When we used exponential function in RO3 model, the reward accelerated initial training but showed unstable tendencies as training steps increased. As you can see in the visualized video, two agents showed different trajectories even though they were initialized from at the same position. Agents have several chances to have similar positions, but they choose different actions because they are trained to penalize the overlapping with previously discovered areas. The left two panoramic images show the observations of Agent 1 and 2. After Experiment 1, we fixed the RO2 model as the optimal mutual overlapping reward and compared self-overlapping models. The results of Experiment 2 are shown in Table 4. Among 3 self-overlapping models, RS3 model, which uses both global and local self-overlapping reward, outperformed other 2 models. Additionally, comparing with the case without self-overlapping rewards, agents were able to explore more in shorter time steps. It is notable that using self-overlapping rewards can increase the time efficiency of visual exploration. In the video, agents explore the same scene in the previous Experiment 1 but cover more area fastly. To conclude, the experiment results imply that mutual overlapping and self-overlapping rewards have a synergetic effect when they are used together in visual navigation. This is the end of my presentation. Thank you for listening to my presentation, and please feel free to ask any questions.